to detect this type of threat, then once the malicious domain, the actual malicious domain that's serving the malware is down, they can't detect anything because they can't actually fetch the PE malware for them to analyze. And JavaScript-based languages are also very, very hard to analyze compared to PE. And so here the playground is ECMA scripts, which include JavaScript, VB Script, Adobe JS, and ActionScript. And so we want to skip this last step and want to use Metasploit, want to serve payload in the form of memory injection. For example, Meterpreter. Okay? And so we're dealing now with, we're focused right now with just script obfuscation for both the exploit and also for the payload. Because right now, the payload is right here. We don't call it droppers anymore because payloads like Meterpreter inject themselves directly into the memory and they do all their stuff in the memory without having to write themselves to disk first. So drive-bys want to avoid detection at the victim's desktop, avoid detection by UTM and gateways, avoid detection by automated monitors, live for as long as possible. This is a very important requirement because when you're using 0 days in targeted attacks, you don't want any security vendor. Maybe you're just targeting 10 people. You don't want any security vendor to know this 0 day until a year later. So how do you do that? So conclusion, reduce exposure. Serve selectively. Avoid detection and analysis. Obfuscate well by obfuscating yourself well. So serving selectively. At the HTTP level, serve only to fresh IPs. So serve to each IP only once. This has become a typical drive-by download behavior. So if you're a malware researcher, unless you're randomizing your IPs, otherwise, like if you're linking from an antivirus IP, they're just not going to serve anything to you. And this option is supported in Metasploit using the data store. And Metasploit supports different databases. Serving only to a particular referrer. For example, in our Dick.com case, if your referrer isn't Dick.com, that means you're trying to analyze me, and I'm not going to serve to you. If your referrer is Dick.com, there's a higher chance that you're a victim visiting Dick.com and then Dick.com loading that iframe. And this option is also supported in Metasploit. Or a particular agent stream. For example, if we're using IE 0 day, and we don't need to serve to Firefox or any other crawlers, Google crawlers, antivirus crawlers, whatever. And blacklist, which means we want to collect a big list of antivirus IPs, and if you're coming from Armorize, if you're coming from Symantec, McAfee, Trend Micro, nope, we don't want to serve to you. Okay. So dissecting and JavaScript exploit. There's a shellcode, there's a memory corruption, there's a heap spray, and there's a trigger. The shellcode is the payload, for example, Meterpreter. The memory corruption is where you corrupt the memory, for example, buffer overflow or other types of memory corruption, and you trigger that vulnerability. Heap spray is first published here at Black Hat by Skyline, and it's just an easy way, a very robust way to exploit the browser. And then there's the trigger, which is the trigger that calls your JavaScript, that calls all these code and activates them and executes them and triggers the exploitation process. So, and this whole thing that we just saw, all these JavaScript code is often obfuscated into a big blob of code that's unreadable and then deobfuscated to its primitive form. So we call the obfuscated form and the primitive form. So as you see in the previous slide, here's obfuscated form and here's the primitive form. So the attackers, what they usually do is they try to randomize the primitive form. And they try to prevent the triggers from happening inside a detector. Okay, so two ways. First, obfuscate the primitive form to bypass antivirus detection. Second is if I am run inside a detector, I do not trigger myself. All the code is there, but it's not executed. So let's talk about the first one, which is the obfuscation, randomization of the JavaScript code. And the first one we implemented was called the JavaScript concat string obfuscation. It's very easy. This is how the payload looks like, and you call the obfuscate.js function inside Metasploit. And what it does is it randomly chops the string because this part. Okay, let me show you. Okay, so here you have script var shell raw equals a big long string, and you want to randomize this string. So what you do is, if you want to simulate this behavior, in Drivesploit, you call the function, and it randomly selects, it randomly chops the string up. You can specify, for example, chop every 3 to 10 characters. And then it assigns these chunks to different variables. And then it scrambles them. It scrambles these variables so that the assignments are randomized. Okay? So, randomized variable, and so basically, and then it concats them together. So this is what it does. It then adds them together to form the actual random string. The addition code here is also randomized, so there's no knowing which would happen first. And so this is the final code. So that's the first thing that we generated. Second is called JavaScript random text insertion. And it's a very used technique. It actually works very, very well. It takes a string as input, and you specify 648, as in this case. You're saying that insert a fixed 6-character random string for every 4 to 8 characters. So it returns a piece of JavaScript containing the injected string, and also a JavaScript variable name containing the reverted original string. So here you have a string. Drivesploit is fun. You call the injection function, and what it does is it generates a JavaScript along with the deobfuscation JavaScript, right? So it generates this string, assigns it to a variable. It also generates the regular expression deobfuscation to take out the randomly generated and inserted string. The third one is called JavaScript random text insertion. And this part is also very important because the numeric literals inside a piece of JavaScript is often the target for antivirus detection. It's often used as signatures. So for example, in the IE drive-by download exploit that we're using as example, there is a hex number that's fixed inside the exploit. And so what you do is you call the Drivesploit function, and it turns that into an arbitrary algorithmic calculation, as you see here. And this results in this number right here. All these are techniques that we've seen in the wild, and so we just want to know which antivirus is good at detecting which, and how good are we at when something like this happens. So with this type of framework, what we can do then is when a new exploit comes out, we can expect that all antiviruses after a week, or most of them, are going to be able to detect that because that's becoming a new, an old exploit. But we want to know the ability for these technologies and for our own to detect new and derived exploits. So we take that exploit and we'll put them into Drivesploit, and we will call these functions, and Drivesploit would then serve variations of the same exploit, which works, and see who can detect what. Okay, and now to the latter part, which is trigger prevention. And these are just some techniques, but they work very well. div unload. So setting your trigger function in div unload. And why that works is a lot of automated detection engines use JavaScript engines such as SpiderMonkey or Rhino that does not implement the DOM. And so when you're setting div unload without the DOM, it's not going to trigger. And the second one, for example, image unload. Anybody want to guess which one's more effective at beating antivirus? Div unload or image unload? Why? Why? That's correct. But why? Okay, so some vendors like us actually run instances of IE like the virtual machine that I just showed you, and they monitor the behavior. However, some of them, including us originally, in order to, because we have to scan millions of URLs per day, so in order to speed that up and to lower the cost, we configure IE to not load images, and they figured this out. So you can run a real IE, but if you disable images to save some bandwidth and to save some computation power, it's not going to trigger, right? So this one, do while. A lot of them use grammatical differences between IE and Firefox, or IE and scripting engines available. So this one, there's a semicolon right here between the bracket and the while. It's not that obvious, but this is actually a grammatical mistake. And so Firefox-based JavaScript engines like SpiderMonkey and Rhino would actually raise an exception here, but IE can take care of it perfectly and keeps on executing. So if you put this in, then in automated detection by a security vendor, it might just raise an exception, while only vendors that run the actual IE would be able to keep running the code. And then browser fingerprinting, which is very, very effective, and which I'm going to show in a bit. So testing it out. So the plain, the one that we selected, the plain exploit, hits 17 out of 42 in virus total. Randomized vars. I didn't talk about this. We implemented a JavaScript parser that parses the JavaScript, your JavaScript automatically. So you call the function give Drivesploit the JavaScript, and it will parse the JavaScript, and then it will extract all the variable names and function names. And that's a very formal parser. And then it will replace all your variable names and function names with random names for you. So it's basically what we call random vars. It's a random variable JavaScript generator, okay? And works very well on existing JavaScript. Unless you have a grammar error, then our parser breaks. And that, however, we were 17. That took us down to 16, and that's why I had no slide for it. So apparently, all the signature-based technologies were not basing their patterns on variable names. So injection source code, so the string injection took us down to 13. And random vars plus concat on shellcode plus injection on shellcode brought us down to 11.